Cool. So this is just a quick math diversion. Math diversion. If this doesn't make sense to you, or if you're not happy with it, don't stress. This is just a little bit of extra for the maths, for the people that enjoy the math. If I was going to graph if this is displacement versus time, if I was going to graph this as, let's just say, a straight line, we could work out the gradient, and let's just say that the gradient is 5 to 1. So in other words, if I was going to write the function of the displacement in terms of time, I would say that the displacement is equal to 5 times t. Sorry, the s and the 5 look almost similar. That's a 5 on the right, that's an s on the left. Cool. So I have a function for the displacement. Cool. Then what you can do is you can take ds by dt, which is the gradient of the graph, or the derivative of the graph, and that would just be 5. But you also know that ds by dt, the change in displacement over time, is the velocity. So can you see that the velocity in that case would be 5? So if I was going to plot this as a velocity time graph, I would plot it as velocity versus time, and it would just be a constant straight line at 5. Cool, everyone happy so far, just in terms of gradients, derivatives, velocity versus time, whatever. Cool. So what's interesting here, have you guys done the derivative of sine? So have you done d by dx of sine x? Have you done that derivative?
No, I don't think so.
You haven't done that derivative. Okay, so I'll tell you now that the derivative of the sine graph, d by dx, is actually the cos graph. It's an interesting property of these two graphs, is that the derivative of the sine graph actually forms the cos graph. So if you want to take that one step further, if this is your displacement graph in terms of a particle, and you look at its velocity graph, what we're basically saying is that if the displacement graph is a sine graph, it means that the velocity time graph is going to be a cos graph. And you don't have to know the maths really to understand this, but what you really have to do is you have to kind of go and sit and think about this. And when I say think about it, don't try to copy, paste, repeat, learn it. What I say is go home and analyze it, and make sure that you understand that there's a relationship between the displacement graph and the velocity time graph, meaning that the displacement graph tells us about the position of the object, or the particle in this case, and the velocity time graph tells you how fast is the position changing. Cool. So there's definitely a relationship between those 2 points. And what you'll notice here is that when it's at its maximum displacement, let's call that x naught, you'll also see that the velocity is equal to 0. Is that what we saw in the previous lesson? Does that make sense?
Yes, sir.
Yeah, that makes sense, because we said that when it's on its end, when we said that if it's a pendulum, and if that pendulum is at x naught, its velocity is equal to 0. So you can see that relationship there, and you'll see it again at this point over here. You'll see when it's at its minimum displacement, or maximum negative displacement, you'll see that the velocity is again 0. So the two graphs correspond. So there's a relationship between the displacement time graph and the velocity time graph. Cool. And then the one that's slightly harder to see, and I'll leave this up to your imagination, is that you have to see that when the displacement is 0, so when it's at its equilibrium point, you'll notice that the velocity is at a maximum. Cool. So this is max v, and this is displacement is equal to 0. In other words, when the pendulum is at its downward point, the displacement is equal to 0, and the velocity is equal to maximum. So you have maximum velocity when displacement is 0, and that's exactly what that graph shows you over there. So it tells you that when the displacement is 0, or when it's at its equilibrium position, it has its maximum velocity. And you'll see it'll tie up in every single point that you look at on that graph over there. So it ties up on every single point over there. So that's the best thing you can do, is you take a picture like this, you put the one graph on top of the other graph, you draw the lines to correspond with the same time period, and you tell yourself what is the displacement at that time period and what is the velocity at that time period. And then if you really want to, you can go and play with the app, and then you can just go and think about it. So you go and play with the app and you just imagine it and you play with it. Hang on, where's the pendulum? There you go. You just play with the pendulum app and you think about it in terms of displacement and velocity. I don't think this draws a graph. I think period trace. No, that's not going to help. There was one that I think used to graph it. Velocity, acceleration. Here you go. You can put the velocity on and then you can actually see what's happening to the velocity. There you go. So the green arrow there is the velocity. And you can see it's changing directions and it's getting bigger and smaller. Cool. So then you can think about what the graph would look like if you were going to plot that against time. Cool. So like you did with the wave project, like you did with the speed of wave project, what you can do as a little side project is that you can go and play with the app, and then you can think about drawing the displacement time graph and the velocity time graph, just as a little project for yourself to keep you busy. Cool. Any questions?
No, sir.
You good? So the best thing to do with it, yeah, the best thing to do with it is to play with it. The only way that you're going to learn it is if you try to analyze it. You're never going to learn it if you literally just put the page in front of you and look at it for a few seconds. It's not a memorization technique. Cool. So you're not trying to remember if this is what the displacement looks like, this is what the velocity looks like. What you're trying to do is you're trying to see the relationship between the velocity and the displacement. Cool. So you've got to analyze it. You've got to sit down and you've got to think about it for a few minutes. Okay. So the AS level, unfortunately, is a bit more specific than the IGCSE. In IGCSE, with the wavelengths of the electromagnetic spectrum, you only really had to know the order of them. You didn't really have to know how big or how small they were. But unfortunately, for AS level, you have to know the actual orders of magnitude. In other words, the size of the waves. And you've got to know it in terms of wavelength, and you've got to know it in terms of frequency. But just before I carry on, let me just ask you a question and let you think about it. Do you have to learn both? Do you have to learn the wavelength and the frequency? Is it necessary to learn both of them?
No, you just need one.
Because you
just need one. Correct. So you guys are one step ahead of me. And if you remember, there's an equation that we can use. If we say that the speed of light is equal to the wavelength times the frequency, they tell you that the speed of light is constant. So if I know the wavelength, if I know this, I can calculate that. In other words, you can basically just learn the wavelengths. You don't have to worry about learning everything. Cool. So you can think of mnemonic devices. You can think of, you know what I mean by a mnemonic device? They talk about like make every letter like as part of the story, and then you say general X used to infer radar TV, or I don't know, something weird like that. You can do weird things like that if you want. But I don't know. I can't really think of a better way to learn it. Cool. But what you can do is when you think of the orders of magnitude, you can think of the distances that they travel and you can kind of relate it to that. So just as a quick, sorry, I need to edit here. Just as a quick reference guide, whenever you think of the wavelength of visible light, it's on the nanoscale. And the reason it's on the nanoscale is because particles are on the nanoscale. So if you think of chemistry, I know you guys are physics, but if you think of chemistry, and if you think of bonds and you think of the distances between electrons and protons and other protons, that's on the nanoscale. So it's more or less on the 10 to the negative 9 scale. So if you can remember that, visible light is a nanoscale. So just tie it in with yourself and remind yourself, visible light, nanoscale. Cool. So that's one solid connection you can make, visible light, nanoscale. Cool. Then you can go to the longer wavelengths to the right-hand side. And you can remind yourself that things like FM, TV, shortwave, AM, they're extremely long wavelengths. And the way you can remember this is that they're going to travel long distances to get to you. So you can think of this communication, this conversation we're having. we're so far apart, but the electromagnetic waves are traveling through the air to get to you. And they're generally radio waves or TV waves or something like that. And they're generally long waves. Also, they're bigger than a meter long. Also, they're the longest waves, and you can think of them as being like on a meter/kilometer scale. Cool. So these ones here you can think of as meter/kilometer scale. Cool. So you think of that as meter/kilometer. Sorry, this is a bad picture because it actually doesn't have microwaves. Microwaves is here what they call radar. So microwaves is here what they call radar. And the way you can think of microwaves is that microwaves fit inside your microwave, and you can measure the length of your microwave in centimeters. Cool. So you can measure the length of your microwave. I didn't record the meeting, or did I?
You did say, I think you did.
It is. I did. Okay, I did. Sorry. Thank you. I'm just thinking. All the stuff I'm saying. I'm hoping that it's on the video, but it will be good. Okay. So radar here is what you would call microwaves. Cool. And you can think of it in terms of the centimeter scale. So if you look here, they say 10 to the negative 2. 10 to the negative 2 meters is equal to 1 centimeter. Cool. And you can think of it as my microwave is about 30 centimeters long, and a microwave in terms of the light, electromagnetic radiation, fits inside the microwave. Cool. So it's on that sort of scale. Cool. And then on the left-hand side where you have the X-rays and gamma rays, they're tiny, 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 tiny. Now you're talking pico and sort of tiny, 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 tiny wavelengths. And you can remember 10 to the negative 12, and you can remember 10 to the negative 14. Also very, 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 very tiny waves. And then you can think of, you can think about, I don't know, something like gamma rays would be gamma radiation, high energy, very, very, very small wavelengths. You can go back to IGCSE and you can remember that these things traveled very short distances, very, very, very short distances before they basically diffused into nothing. So very, very, very small. Cool. So you've just got to try and find some clever ways to remember that. And if you find something on the internet that you find is useful, then you can post it on the group so that everybody can see it. If you find a useful way of remembering these things. Cool. Any questions? Any concerns? Questions? Anything you'd like to ask or talk about? Yeah, Angelica, go for it.
So do we need to know the range, or is like the one on the picture specific?
You need to know the range, correct? So this was a terrible picture. Let's see if I can find a nicer one. Let's see if there's I think this is a nicer looking picture here. Yeah, here we go. So let's have a look at this photo quickly, see if this looks nicer. Yeah, there we go. That's a nicer photo. Yeah, it basically goes in orders of about 2 to 4. So the changes are often steps by 2 or 3. So that's one way of noticing it. So very good observation there. The steps are quite small usually. So here you can see microwaves. Here they've actually got the word microwave, and 10 to the negative 2 is a centimeter. So if you remember that 10 to the negative 2 is just a centimeter, and you can think of your microwave oven. So you think of your microwave oven, it's about 30 centimeters long. So your microwave oven is quite small. Cool. Radio waves, you know that they travel a long distance, so they're very long waves, and 10 to the 3 is just a kilometer. So 10 to the 3 is just a kilometer because they travel kilometers of length. Cool. Then you remember visible. Visible is on the nanoscale. And it's difficult to imagine this, but you can think of nanotubes or nanotechnology. It's stuff that's just barely visible from a microscope. So you can't see nanoparticles.
Yeah, you can think about biology.
Yes,
like we usually use nanometers.
Exactly.
Cells.
Correct. And it's often, and the reason because you can see the cells is because they're on the size of the nanoscale. So they're visible to the naked eye. If they were smaller than the nanoscale, we probably wouldn't be able to see them in terms of visible light. So anything that's visible is on the nanoscale. Cool, and then UV, X-ray, gamma, you can see that it shifts approximately by an order of 10 to the negative 2. So the change is approximately 10 to the 2. And then UV is just.
So?
Yeah, once you know the range.
So once we know the range, we just click it in our calculator in relation to the equation of light.
Correct. So you'll see here. You'll see here that if ultraviolet is 10 to the 8, you can say that C is equal to 8. Sorry, not 8. C is equal to 3 times 10 to the power of 8. That's the speed of light. You've got to remember that it's a constant on your data sheet, so it is available. You don't have to remember it off by heart. Cool, then you can say that C is equal to wavelength times frequency. You have this value here, 3 times 10 to the negative 8. Then you can plug in a wavelength, let's say 10 to the negative 8, and then you can solve for frequency.
Okay, so you just minus 8, right? Minus
something like that. Yeah. Correct. Because you're going to see that it's going to invert the sign. So what's a very, very, very tiny number in terms of wavelength is going to become a really, really, really big number in terms of frequency. Sorry, this is not a negative 8. Sorry, this is a positive 8. That's a positive 8 there. So it's going to go up to 10 to the 16, which makes sense because that's what they've told you over here. Yeah, so something that's very, 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 very small on the wavelength scale is going to be very, very, very big on the frequency scale. So you just got to think of your indices, your laws of indices. Are you going to add the index or are you going to subtract the index? And in this case, Gloria is correct. You're going to add the index on the left-hand side. Cool. And then I think Angelica asked a very good question. And then I'll show you the example questions. You can have a look here. M and N on 2 electromagnetic waves. Oh, sorry, the screen stopped sharing. Sorry, I'm going to share the screen again. iPad share. Screen mirror. It's not picking it up. Give it a second. Sorry, let's just reset. Share. Screen mirror. Technology. In any case, there's a question that's in the past papers, and it's basically asking you, there's a ratio of 2 waves, and then it's asking you what are the possibilities of those 2 waves, and then they give you options in terms of X-rays, microwaves, whatever the case is. And remember that it's an approximate range. It's not like you have to have an exact value. It's one of those things where, because everything's off by about 10 to the positive 3, your answer will be within a range of approximately, let's say 1 order of magnitude bigger or 1 order of magnitude smaller, depending on your approximation. So let me just quickly stop the share here again and then see if I can share it one more time. If it doesn't work, I'll tell you the question number and you can go have a look at it. Go. There we go. Cool. Can you see the question now?
Yes, sir.
Yes.
There we go. So here's the question, and it says that M and N are 2 electromagnetic waves. Excuse me, sorry, I want the highlighter pen. M and M are 2 electromagnetic waves. The ratio of M to N is 10 to the power of 5. And it says suggest 2 possibilities for M and N. So you've got to estimate, and you've got to say, well, microwaves are approximately 10 to the 2. So, whoopsie, not that one. Let's have a pencil. If we're going to do A, let's do A. If M is 10 to the negative 2, visible, we're going to say is approximately 10 to the negative 6 because it's approximately on the nanoscale. The question is, what sort of ratio would this give us? So this is 10 to the negative 2 times 10 to the positive 6, which is approximately 10 to the 4. So this is a possible answer. Then you can just keep checking. Now you can definitely eliminate B because gamma rays are going to be so small that it's going to make it much bigger than 10 to the negative 5. So if we did gamma would be, let's take away that. Gamma would be even smaller. This would be like 10 to the negative 14. This would become 14 over here. and this answer here would become 10 to the 12. So it definitely can't be B. So A sounds about right so far. Well, then you can take gamma over micro. Gamma over micro is literally going to be the inverse of this. And the ratio is literally going to be the inverse, which means that this is going to be a negative 12, a negative 4, based on our previous calculation. So C is out. Ooh, and then you can do visible over micro and see what you get there. Ooh, and then visible over micro is also going to give you a negative number. So that won't work. Also, the answer in this case is A. Cool. So I'll show you that again one more time. I'll neaten it up and then I'll do that just one more time. So I approximate micro. I approximate it as 10 to the negative 2. I approximate visible as approximately 10 to the negative 6. And that gives me approximately 10 to the negative 4. Cool. If you were going to do D, D would be 10 to the 6 over 10 to the negative 2, which is going to give you 10 to the negative 4. So that's wrong. So D is off. And then micro and gamma, the difference between micro and gamma is so big that it's going to be definitely bigger than to the power of 5.
So I have a question.
Sure, please do.
Here in the multiple choice, they we can use the estimation. Now in the structured questions, will they like tell us it's 10 to the power of 5, or should we just go off our?
In the structured questions, they'll never ask you to estimate. In the structured questions, they'll give you a value. So in the structured questions, they'll say a gamma wave with wavelength of so much is emitted, calculate its frequency or something like that. So in the structured questions, you'll never get asked to estimate. And if they do ask you to estimate, you can give a range. You don't have to give an exact value. But I doubt they'd ever ask you to use it in a calculation where you have to get a final answer, because then everybody's answer is obviously going to be different depending on the approximation. Mm-hmm. So they could, here's like an example for a structured question. They could say a wave has an approximate wavelength of 10 to the power of negative 2. And then they're going to use the word here, suggest suggest which type of wave it is. Ooh, and then your answer will be 1 mark just for the suggestion. Ooh, and in this case, it would be microwaves. So in that case, that'll be the answer. But they would never ask you to estimate and then use that same estimate in a calculation, because that wouldn't make sense, because otherwise everyone's answer is going to be different depending on the approximation. Ooh, and then you can see there's a couple more of these. Period of an electromagnetic wave is that. Calculate its frequency and wavelength. That's quite easy. You just plug it into the equation. C is equal to that times that. And you remember that this is 3 times 10 to the power of 8. It's a constant. So that's just for that. Here we go. 3 different electromagnetic waves, P, Q, and R, have frequencies over here. And then it says identify them in terms of which ones they are. And in this case, you could probably get away with just remembering the order. In this case, you probably don't have to remember the range. You just have to remember in what order they appear. And then you just say which is the lowest frequency and which is the highest. So highest frequency would obviously be gamma, and lowest frequency would be something less than gamma. So possibly, possibly something like micro or somewhere around there. But you can already see by process of elimination, if R has to be gamma, answer has to be C. Which makes sense because it has everything in the correct order. It goes ultraviolet, X-ray, and then gamma. Cool. D kind of works. D is in the correct order. D is another possibility. The problem with D is that visible light is not so big. Visible light is approximately 10 to the 9. So visible light we know is approximately 10 to the 9. So you've just got to play around with, you've got to think of smart ways of remembering these things. Cool. Then there's one last question that Stefan asked at the end, and then I told him that I had a different question I wanted to focus on. It's this one over here, and it says the graph shows the displacement of a particle of a wave, and then it says which statement is correct. You can work about the period and stuff yourself, But the question of whether it can be either transverse or longitudinal, what I want to tell you is I'll give you the answer. It could be transverse or longitudinal, because remember, it's not the wave itself, it's the function of the displacement. Ooh. So would you agree with me that this could represent a particle that's doing something like this? Ooh, it could be doing something like that, where it's going 2 centimeters to the left and it's going 2 centimeters to the right, and it's displacing over time. So the graph itself can represent either transverse or longitudinal. Well, does that make sense?
Yes.
Yeah. So it's not this itself is not the wave. This graph is not a wave. This is not a wave. Ooh, it's a displacement time graph. Ooh, and it's telling you that the particle is being displaced. And in other words, that particle could also be being displaced vertically up and down. 2 centimeters up and 2 centimeters down, in which case it looks more like the wave on the string or the rope or whatever the case is. Cool, and then you can go figure out what the period is. You can go and do that as a finish off. Cool. So as far as the basics go, you can basically answer all of these questions now. So that's what you're going to do for the rest of the day. We won't have a second lesson. You can just work on all the questions.
Okay, so
cool. So no second lesson.
So you send the mark scheme.
I'll send the mark scheme. Yeah, I was busy working on it last night, but I completely forgot that I have other questions, like the oscilloscope questions and stuff that I still need to do as well. So I'm busy ticking it off one by one. Ooh, but I'll finish this mark scheme and I'll send it later. But yeah, that's your second lesson. Let's call it work to do. We're not going to have a lesson.
Okay, so.
Cool. And then during the second lesson, I don't know what time it is. I don't have my timetable with me. During the second lesson, please feel free to contact me. That's your time. That time belongs to you. So if you have any questions during the lesson, please WhatsApp, email, tell me to come on Zoom, Skype, whatever. Just get hold of me during the lesson if you have to.
Okay, so.
Cool, guys. Have a good day. Be good. I'll see the rest of you in chemistry.
Yeah.
Bye, sir.
Bye, guys. Be good.